Okay, so we're going to have some sort of a chapter jump from chapter 4. The next chapter that we going to discuss is chapter 7. Okay. Now, there's a reason in doing this is chapter 7 because it's just a continue in the atomic structure that we have discussed in chapter 2. Remember, we end up with the atomic structure there being the nuclear model by Ernest Rutherford. So that's the last we could say model of atom that we have discussed. Now, in Rutherford model of the atom, just want to make sure it's recorded. Okay. In Rutherford nuclear model, the atoms consist of nucleus with electron occupying the remaining space. So the nucleus, they are many times smaller than the atom itself. Okay, so it's being surrounded by electrons, but usually it is an empty space, okay, occupying there. So the question that you can ask is, how are electrons distributed in space? What are the electrons doing in the atom? Okay, so if that is the case, then there are we could say several questions that come out based on the model that's proposed by Ernest Rutherford. Okay, and assuming the molecules behave like these rebounding balls, it was able to predict and explain some macroscopic phenomena. Okay, and how can they account to the so-called stability of molecules? Now, the question here is, why can the physics at that time cannot explain the forces that hold atoms together? Okay, so to answer this question, they have to think outside the box. Okay, so there are some explanation that they look. So they looked at the atoms in terms of microscopic view. So the structure of the atoms relevant to chemistry. There are electrons around the nucleus. That's Rutherford model. Okay, so for them to determine this thing, they have to know the so-called concept of the wave. So when we talk about wave, this is a continuously repeating change and oscillation in a manner, in matter or in a physical field. Okay, we could say a wave is what? A vibrating disturbance. By which energy is transmitted. So if you're going to look at this wave that we have, okay, so let's say if you are in a pond, you throw a stone on it, it will form something like this. Now, if you're going to look at the cross section of that, it would be like that one. So that's the wave that we know. Okay, and the thing that they look at the wave is the so-called light. They say light is made up of what? Electric and magnetic component, electromagnetic wave. So it's consisting of oscillations in electric and magnetic fields traveling through space. Okay, so If we're going to look at this wave, we could say it is characterized by its wavelength and frequency. So wavelength is just the distance, okay, between any two identical points on an adjacent wave. It can be the peaks here, it can be the trough, as they call it, the lowest point, or any identical point that you have. And usually, if you have a wave, it is what we call described by lambda. Okay, wavelength. So that's one characterizations of a wave. So if you're going to look at the wavelength, the distance between identical points on successive what we call wave. Now, if we're talking about the vertical distance from the middle wave to the peak or the trough, this one or this one, that's what we call amplitude. Okay. Now, another characteristics of a wave is what we call the frequency. So frequency, as symbolized by the Greek letter nu, that's the number of wavelength that pass through a fixed point in 1 unit of time. So usually a second. So the unit of frequency or 1 per second is called the hertz. So if you're going to look at the wavelength and the frequency, they are related by the speed of light, which is equals to 3.00 times 10 to the 8. So speed of light is the product of frequency and wavelength. And the relationship between wavelength and frequency due to constant velocity of light can be illustrated in the next slide, on the next slide. Okay, so if you're going to look at this, what's the difference between the two? They have different wavelength. Okay, so if you're going to look between the two, the wavelength that you have here, okay, longer. So as you're going to see, this is longer because this one is from here going here compared to this one. However, if you're going to look at the number of frequency, so in a given point, which is from here to here, that's the second, you can only have how many frequency here? You only have 2 hertz. Compared to this one, that is a shorter wavelength, you have 4 hertz. So if we're going to look at this, okay, between the two, when the wavelength is reduced by a factor of 2, the frequency increases by a factor of 2. So there's an inverse relationship between the wavelength and the frequency. Okay, now, how do we look at the problems in this chapter? So this is how we look at the problems here. So what is the wavelength of blue light with the frequency of 6.4 times 10 to the 14 hertz? So if we're going to look at here, so you're given the frequency and indirectly the speed of light, 3.00 times 10 to the 8 meters per second. So if you're going to look at it, this is the relationship that you have. So what are we going to do? This one is given, this one is given. So you are asked for the wavelength here. So you rearrange themselves. So put on the given value that you have there, 3.00 times 10 to the 8 meters per second divided by 6.4 times 10 to the 14 per second. So the one that's cancelled is just a second. And you have there an answer that is in meter. So that would be 4.7 times 10 to the negative 7 meter. So easy, right? You will be given the formula like this one. And the value of the speed of light. Now, as you're going to see, so the problem that we have is C is always a constant, and you're given the frequency, and you are asked for the wavelength. Okay? Now, you can still convert this to nanometer. So 4.7 times 10 to the 7 meter. If you convert it to nanometer, so for every meter, you have 1 times 10 to the 9 nanometer. So you end up with 470 nanometer. Okay? Now, I told you the next question that you can have here is instead of the hertz that is given, what if the hertz is the one being asked and the wavelength is given? Just like here, what is the frequency of light having a wavelength of 6.81 times 10 to the 681 nanometer? So what you're going to do is you need to convert this to meter. And in doing that, you can just use 681 nanometer times for every 1 meter, you have 1 times 10 to the 9 nanometer. And you end up with 6.81 times 10 to the negative 7 meter. And once you have that, you look at the formula. So the one that you're looking for is the hertz. So you divide both sides by the length, the wavelength. So 3.00 times 10 to the 8 meters per second divided by 6.81 times 10 to the negative 7 meters. So you could see the unit that you have there is per second, and this is equals to 4.41 times 10 to the 14. Please check. Because I want you to have sure points in this what we call type of question. Question. Now, to give you an idea where we find the 681 nanometer, I'm going to introduce you to the so-called electromagnetic spectrum. Okay, so this is the electromagnetic radiation. So the electromagnetic radiation, so this is the one that allows us to tell with regards to the atomic structure. So if you're going to look at here, the different region, so there is a small region here that allows us to see, okay, this visible spectrum. And if we're going to look at the other electromagnetic radiation, so we can go from the shortest to the longest, or from the highest frequency to the lowest frequency. So shortest wavelength, we could say the gamma rays, the X-ray, okay? So they're going to longer wavelength, the far UV, the near UV, and then we have the visible region. The near infrared, the far infrared, the microwaves, the radar, and the radio waves. Okay? Now, as much as possible, I remove questions with regards which of the following is longer. But I cannot do it in here. So if I'm going to reverse this one, like the rainbow of the color, how do you pronounce it? Roy G. Biv? So what information we can get from this, what we call Roy G. Biv? Anyone? What information that we can get here? So this R is the longest wavelength, and the violet is the shortest wavelength. Now we can also look at in terms of the frequency. So this is the one that has the lowest frequency, and this is the one that has the highest frequency. So those things, you may be asked question like that in your chapter quiz. So which is longer between red and yellow? Okay, and indirectly here you could see also the energy. So which is more energetic? Which is more energetic? The blue flame or the yellow flame? Anyone? Which is more energetic? The blue flame or the yellow flame? Hmm? If I ask you a question, which is more energetic? The blue flame or the yellow flame? Anyone? Maybe we can ask it in terms of this one. Which is more energetic? Is it the blue flame or the yellow flame? They always said it what? Cool blue. Okay? So to the one who answered that question, you're right. The one that is more energetic is the blue. And you can explain it by the Roy G. Biv. So as you could see in the Roy G. Biv here, so the blue flame is around here. It has what? Shorter wavelength compared to the yellow flame. So if you have shorter wavelength, okay, that means you are high energetic. Can we look directly in the sun? Usually we cannot look directly in the sun because the sun can destroy our eyes because it's more energetic. And what is sun? Sun is your UV, right? If you expose yourself during the summer and sunbathing, what do you get? You get tan. But when you get tan, it burns your skin. So that's what it means. Okay? The shorter the wavelength, the more energetic it is. Now, if we're going to look at the property of a wave is they can undergo diffraction. So when we say diffraction, they spread out when they encounter an obstacle about the size of the wavelength. And in 1801, Thomas Young, a British physicist, showed that light could be diffracted. So we could say by the early 1900s, the wave theory was well established. However, the wave theory could not explain the so-called photoelectric effect. Okay? Now the question is, what is this photoelectric effect? So the photoelectric effect is the ejection of an electron from the surface of a metal or other material when light shines on it. Now the wave theory of light cannot explain this phenomenon. Okay, so what one of the great person with one of the greatest mind did is Einstein proposed that light is consists of quanta or particles of electromagnetic energy that he called the photons. And he said the energy of each photon is proportional to its frequency. So the way that he did here is he just applied what was known during that time as the Planck constant in explaining the phenomena. So instead of saying it's a wave, he said that it is a particles of electromagnetic energy. And he said each of the photon is proportional to its frequency. So he used the Planck constant. So energy is just equals to Planck constant times the frequency, and the Planck constant is this one. And again, you don't need to memorize them. It will be supplied to you. All the formulas that we have here will be supplied to you, at least in chapter 7. Okay? So if I didn't say anything, most likely it will not be supplied to you. So, but here I'm telling you now, all the equation or formula that we have in chapter 7 will be given to you. So what Einstein did is he used his understanding of light to explain the photoelectric effect. So he said that each electron is struck by a single photon, and only when the photon has enough energy will the electron be ejected, that photon said to be absorbed. He was right because he was given the Nobel Prize. Although Albert Einstein is more known for his theory of relativity, he got the Nobel Prize from this explanation. Okay, explanation on the photoelectric effect. So what does it mean? It means that there's a dual nature of light. It can behave both as a wave and a particle or matter. Okay, and neither understanding is sufficient alone. So what everyday example we can compare this dual nature of light. Maybe during this time, summer, if you go to the beach, so if you are in the water part of the beach, if you're going to look at the beach, it's just a one straight coastline. Okay, it's just like a wave. But when you get closer, you could see that it's made up of particle of the sun, which is usually this is we could say the wave nature, and this is the particle nature. So you have the dual nature of matter. Now that we have this Planck constant, okay, oops, I think I think it's good. Before I'm going to explain to you here, but I have to remove some of the things which I didn't remove on the previous one, just to explain to you what uh, how did we end up with this dual nature of things. So what you're seeing here is how they end up with this what we call dual nature of matter. So as I've told you, the electromagnetic radiation, the way that we look at it is in terms of wavelength, okay? So the longer one going to the shortest one, and the corresponding wave number, but we're not going to look at the wave number, we look at the frequency. So as you could see, the longest one, they have the lowest frequency. And in terms of energy, they also have the lowest energy. Now, just to give you that this electromagnetic radiation, they have their everyday application. Okay. So if you're going to look at the longer wavelength, you have the radio waves. Those are the bases that you have with the AM and FM radio. Usually they are identified by their frequency, hertz. I don't know if you're still familiar with what a radio is. Okay. So the microwave is included on that. Okay. And then you go with the infrared and the applications that you have there in the airport, in the screening. Okay. It's usually in the microwave and terahertz region. And then, as you could see, the visible region is just so small. That's the one that allows us to see the different colors that we have. And if we have suntans, it's just around 400 to 290 nanometer. Okay. Now, as we go on here, X-ray, so you know X-ray is really highly energetic. And as much as possible, don't expose yourself to X-ray as often as possible. Don't do it. And then the gamma rays that we have here, that's also what we call highly energetic. If you are exposed to it, you're not going to turn to incredible Hulk. You're going to die. The same thing with the cosmic rays. You're not going to become the Fantastic Four. You're going to die because of the high energy that we have. So this is, we could say, the chart of the electromagnetic spectrum. Now, the revolutionary study that they said changed how they look at science is the so-called black body radiation. Okay. So in the black body radiation, you have there the so-called black body. So the black body is a perfect absorber and emitter of radiation. and usually we can look at it as heated solid, the spectrum of heated solids. Now, this cannot be explained by classical physics. Okay? So what happened? A guy named Planck, Max Planck, proposed that for the black body radiation to be explained, you have to say that energy is discontinuous, or energy is, the term that he used there is quantized. Okay, so he says there, the smallest non-zero value for energy differences, that's the quantum energy. So the energy of a system has only a discrete set of values or multiples of quantum, hence giving you this formula. H there is named after himself, which is the Planck constant. So what does it mean? Okay, so the radiation will only absorb energy at a certain value, and usually it is, we could say, a multiple of the discrete set of value. So that's where the dual nature of light was first explained. So it's a revolutionary idea by Max Planck, and it tend to explain the behavior of matter that cannot be explained by Newtonian classical physics. Okay, so in terms of the photoelectric effect, where electrons are ejected from the surface of certain metals exposed to the light of at least a certain minimum frequency. Okay, so if you apply the frequency, let's say that is equivalent to 680 nanometer, there's no electron that's ejected. But if you apply 550 nanometer, so there are some electrons that's ejected. But if you go further with 420 nanometer, there are more electrons that is being ejected. So we could say here it meets the minimum energy it needs to eject. Now, if you're going to compare it with a different electromagnetic radiation, so your infrared here, there's no electron because it's not highly energetic. For the visible and the UV vis, maybe some electrons are emitted. But if you have an X-ray and the gamma rays, you're going to emit the electrons because there are a lot or high amount of energy that you have there. And because of that, they come into the realization that they have to have some sort of a boundary between the classical physics and this what we call quantum domain. So the classical domain, this is Newtonian, and you're going to encounter this when you take your physics 1, physics 2. So it explains the big item like the sun, the planet, the quantum fields. So that's the reason why they cannot explain Rutherford model. Okay, how the electron maintains its stability in a given atom. That cannot be explained by Newtonian physics because it says there at lower or a smaller dimension like the photons, the electrons, the atoms, the one that is dictated there is the quantum domain. So there's, we could say, a boundary between the two. So that's the story that they have during that time. And Max Planck is, we could say, honored today because most of the research institute around Germany is named after him, Max Planck Institute of whatever field of specialization. Okay, so let's try to solve this one. The blue-green line of the hydrogen atom spectrum has a wavelength of 486 nanometer. What is the energy of a photon? So what do we know so far about the equation? Because the only thing I'm going to give you is this. And this one. So it's up to you to determine the other one. Like for instance, this, you have to combine the two. So how are you going to combine the two? What is common between the two equation? So you have here both, no, not that one, this one, the frequency. So in this case, you rearrange it in such a way that the frequency is equals to what? C over wavelength, and you end up with HC over wavelength. Try to see, because this thing will not be given to you. You have to derive this from these two given formula. So ask yourself, can you do the math yourself? So can you answer the question based on the given here? So how are we going to answer the question here? So we're given the wavelength, you're given the C, and the Planck constant. So what you have here is E, H times C over the wavelength. So these are all constant, and this one is given. So if you're going to replace this thing, 6.63 times 10 to the negative 34. So that's usually joules second. And then 3.00 times 10 to the 8 meters per second divided by 486 nanometer, which you need to replace to for every 1 meter, 1 times 10 to the 9 nanometer. So cancel the unit. So you have here joules, which is a unit of energy, and that would be equals to what? 6.63 exponent negative 34 times 3 exponent 8 divided by 486 divided by 1 exponent 9. So I have 409 times 10 to the negative 19. Okay? So now that we explained the stuff that we have here, we're not going to apply this to the atomic structure. Okay? So as we mentioned before, okay, the problem of Ernest Rutherford is the classical physics cannot explain the behavior of this atom. Okay, so one thing that they ask themselves is, how can the atom be stable because classical physics says if anything that revolves around a particular thing, there will come a time that it start revolving and it will collapse. But they cannot explain it during that time because, as you could see, the Newtonian physics that they are applying to that atom is not the appropriate explanation. But it takes a while for them to realize that the explanation that they're looking for is not being able to be explained by the Newtonian physics that they have. So it takes a while for Max Planck concept to be what we call accepted and found to be correct in that explanation. Because usually it's a trial and error during that time. So they're not sure, okay, if what they have is correct. Okay. So in the early 90s, when the Rutherford nuclear model is the one that is generally accepted, okay, the atom was understood to consist of a positive nucleus around which electrons move. Now, the explanation of the Rutherford model left a theoretical dilemma. According to the physics of the time, which is Newtonian physics, an electrically charged particle circling around a center would continually lose energy as electromagnetic radiation. But they found out that the atoms are stable. So if you're going to look at this, so there's some sort of anomaly. Why is it behaving different from what it is expected to behave? Okay, and in addition to that, there are some concept or what we call phenomena that they could not explain. For instance, the line spectra of the atom. Okay, so if you have a continuous spectrum, that's your rainbow, it contains all the wavelengths of light. However, when they look at the line spectrum of some elements, they only show certain colors or specific wavelengths of light. So when the atoms are heated, they emit light, and this process produces a line spectrum that's specific to that. And this is the basis of your experiment 10. Okay? So these are what we call the line spectrum. So how come each element has a distinct line spectrum? So for instance, hydrogen, they just see their what? 4 lines. Helium, they see 1, 2, 3, 4, 5, 6 lines. Lithium has 4. And then sodium has 1 intense line. Okay? So that cannot be explained also during their time. So what happened? So they always try to find a way to answer some stuff that cannot be explained during that time. And it takes Niels Bohr in 1913 to account for the stability of the hydrogen atom and at the same time explain the line spectrum of the atom. Okay, so Niels Bohr proposed how can atom be stable, and he tried to propose also the line spectrum of the atom. And just like what others do, he used the concept that the energy levels are quantized. So he said an electron can only have certain energy values called energy level. So for an electron in the hydrogen atom, the energy is given by this equation. So try to look at this one. It's just like some sort of a derivative of this. Why? Because you have there a fixed unit, which is your Reinberg number. And n there is defined as the principal quantum number. So his explanation about the stability, and at the same time, the line spectrum is whenever an electron changes energy levels by absorbing energy to move to a higher energy level or emitting energy to move to a lower energy level. So what does it mean? If you are an electron, you can change energy levels. Okay. So let's say you have different energy level. First, second, third. So if you're an electron, you can move, let's say, if you're here, you can move there, you can move there if you absorb energy. Okay. Or you can also emit energy if you're here, you go here, or you go to that energy level. So during that time, they found out that his explanation made some sense. Okay. So in one way or another, it was able to explain the so-called line spectrum. And what it did here is for a hydrogen electron, the energy change is given by this one. The final energy level minus the initial energy level. Or if you're going to look it in terms of the quantum number, you have a Reinberg equation, the Reinberg formula there, or the Reinberg constant equals to, or times 1 over the final quantum number minus 1 over the initial quantum number. So if you're going to look at this one here, the energy of the emitted of absorbed photon is related to delta E. Okay? So the energy of the photon and the change in the energy of the electron, it just follows some sort of Planck constant relationship. So if you're going to combine the two, you end up with this relationship. So what does it mean? Light is absorbed by an atom when the electron transition is from the lower to higher end. And in this case, the delta E is positive. So it is absorbed. If the electron moves from lower to higher end, the energy is absorbed. That's energy being positive. Now, if the electron transition from a higher quantum number to a lower quantum number, the energy will be negative because there's emission of light. Okay, and from this he ended up having like a energy diagram, energy level diagram for the hydrogen atom, like this one. So each of these transition that you see here, that represent your line spectrum. So if you're going to look at here, this is what? The hydrogen, and this is the basis of your experiment 10. So he was able to explain that this light here, okay, or line spectrum, the line that you observe here, that's just the transition, at least from n5, n equals to 5 to n equals to 2, okay? And then n equals to 4 to n equals to 2. So that's the one that you have here. And then you have n. So we could say this is the one that you observe. I'm going to put here 1, 2, 3, 4. And this is 1, this is 2, this is 3, and this is 4. So the transition that you have here, you can observe it in terms of the line in the line spectrum. So if you're going to look at here, you're going to observe this in the visible region like this. Now there are other transitions that you have, but you don't observe them because ultraviolet, you cannot see it, and the infrared. So the Fashion series is in the infrared region. The Lyman series is in the UV region, while the one that we observe in the visible region is the so-called Balmer series. So in one way or another, he was able to explain the line spectrum. And the model that was come out of this explanation now becomes like the so-called planetary model. So what we had there, there's still a nucleus, but the electron are in some sort of an orbit, and each orbit can be assigned with a quantum number. N is equals to 1, n equals to 2, n equals to 3, n equals to 4. And if you move, let's say, from n1, n equals to 1 to n2, that's where you absorb energy. And if you move from n equals to 4 to n equals to 1, then that means you're going to emit energy. So that's the explanation that it has. And we can have a calculation here to observe where are you going to observe this line? Spectrum. Okay, so what is the wavelength of the light emitted when a hydrogen electron in when a hydrogen when an electron in a hydrogen atom undergoes a transition from n equals to 6 to n equals to 3. So we can just put here E equals to the negative Rydberg constant, then 1 n f squared minus 1 n initial squared. So if you're going to put the values that we have here, we can put the Rydberg constant here, negative 2.179 times 10 to the, what's the value that we have there in the Rydberg? 8. There's something wrong here. But anyway, I just want to make sure I get the right Rydberg constant right. Because there's a lot of value of the so-called Rydberg constant. Because the one that I have here is to the negative 18. Anyway, I'm going to put the constant that we have there, so you don't need to memorize that. So what is n? Which is which here? Where will I put 6 and where will I put 3? So this is the delta E. So I'm going to put 3 there as the final and 6 as the initial. And from here, I can get a negative 1.816 times 10 to the 18 joules. Now, the one that is being asked is wavelength. So what's the formula that we have here? E equals to hc wavelength. So if you're going to rearrange it, it will be hc over the energy. So if we're going to follow through with this one, so you have this, then the Planck constant 6.626 times 10 to the negative 34 joules per second, and then 3.00 times 10 to the 8 meters per second, and then you're going to divide it with the energy that you get there. But you can just use, we could say, an absolute value. You don't need to apply to put it a negative. It's just telling you that there's an emission of energy. That's what the negative value means. So if you get that, what's the answer? So this is joules. So this one is cancelled. Second is cancelled. So you have there 1.094 times 10 to the negative 6 meter. So if you're going to look at it in the wavelength, So you convert it to nanometer. That is equals to what? 1,000. Now, let's try to look where it is. So 6 to 3. So that's the one that is this one. And you don't see it in the visible region because its wavelength is 1094 nanometers. So that's in the Fashion series. Okay? So if you're going to look at this transition that you have here, you can also look at it in terms of this. A minimum 3 energy levels are required. So this is a transition from n equals 3 to n equals 2. And this is a transition from n equals 2 to n equals 3. Okay. So as you could see here, there's a smaller energy difference between this and this compared to this and this one. And it tells you about how energetic it is. Because I can ask you the question here, which is more energetic, this transition or this transition? So the smaller, we could say energy difference that you have here corresponds that it is less energetic compared to the one that we have here. So Max Planck was able to explain the line spectrum. Now, with regards to the model of the atom, they found out it is true, but only if you have a hydrogen atom. So the planetary model of Niels Bohr is only applicable if you have hydrogen atom. But if you're going to look at what we have done so far, which started with Max Planck with the black body radiation, wherein vibrating atoms only have certain energies, and then Einstein, where energy is quantized in particles called photons to explain the photoelectric effect, and then now by Niels Bohr, all of them we could say is a derivative to the idea that's brought forth by Planck. Now, having this dual nature of matter, what we call light, Louis de Broglie also proposed, what about the matter? Maybe we can apply the dual nature also of matter. Because if we're talking about matter, it's always what? Particles. But he said it's possible that matter can also have wave property. So what Louis de Broglie did is he reasoned out that particles or matter can also have wave properties. And he came up with the formula wherein the wavelength of a particle of mass and velocity is given here. So again, we use, look, the Planck constant. So to determine the wave-like property of matter is just Planck constant number, the Planck constant divided by the mass times the velocity. So that's how they do in science. Once they have this what we call constant, they can use it and see if it can explain the phenomena, some phenomena that cannot be explained from that time. And it is best seen here in this example. If you're asked to compare the wavelengths of an electron traveling at the speed of light, that is 100 of the speed of light, and a baseball of mass of 0.145 kilogram having a speed of 26.8 meters per second, or 60 meters per hour. So if we're going to do the formula here, so it's just this one. And if you're going to solve this, so this 6.626 times 10 to the negative 34 joules per second, and then you get the mass. So it says here, an electron traveling at a speed that is 100 of the speed of light. So we have to know the mass. So that's equivalent to 9.1131 kilogram. And then 100, so that's just 3.00 times 10 to the 6 meters per second, not to the 8. And you end up with this value. And if you get it with the ball, the same thing. And then you have the mass, and then the speed. And if you get the value here, it's 1.71 times 10 to the 24 meter. So as you could see, it's so short to the point that you cannot observe the wave properties of a given matter. Okay. Now, if we're going to look at the example of the dual nature of light, and now here matter, how do we observe this? Do you play string instruments? So sometimes what happens, if they're vibrating, you don't see the particle nature. What you see is the wave property. And also, when you took some camera, what happened? Some of the camera or some of the image came out blurry. What do you cause that blurred images? So usually it's some movement that you have done. But that's synonymous to your wave-like property. Okay? So from de Broglie's work, what Erwin Schrödinger did is to devise a theory that could be used to explain the wave properties of electrons in atoms and molecules. Okay, so this is now where you have the Schrödinger and his famous cut thing. So what Schrödinger do is he used the wave properties of matter and apply it to the electrons in atoms and molecules. And he devised a branch of physics that mathematically describes the wave properties of submicroscopic particles. And that's what we call quantum mechanics or wave mechanics. Now, the thinking of this wave quantum or wave mechanics, it alters how we think about the motion of the particles. And then in 1926, Werner Heisenberg showed that it is impossible to show with absolute precision both the position and the momentum of the particle. Okay, so that's just your Heisenberg uncertainty theory. So because P is equals to mv, this uncertainty becomes more significant as the mass of the particle becomes smaller. So what the quantum mechanics or the wave mechanics tells us is we cannot determine exactly where the electron is in an atom, but we can make statistical statement about the regions in which we are most likely find the electron. Okay, so solving the Schrödinger equation gives us a wave function which is psi. So this gives us information about a particle in a given energy level. So the psi squared, it just gives us the probability of finding the particle within a region of space. Okay, so if you're going to look at this psi squared here, with the wave function, as you're going to look at here, as the size increases, the probability of you finding it decreases. So its value is greatest near the nucleus, but it rapidly decreases afterward. So this is the distance of your electron from the nucleus. So as you go away from the nucleus, the probability of finding your electron decreases. Okay? It never goes to zero. It only goes to what we call a small value. So what's the basis of this one? So this is what we end up with the so-called QMM, quantum mechanical model of atom. Okay, so if we're going to look at some illustration here, so this figure tells us the probability density for the electron in hydrogen. So what does it mean? The darker the shades that we have here, the more likely we're going to find the electron. Okay, the concentric circles represent successive shells. And if you're going to view it, okay, of finding the probability here of the electron at various distances, so this is how it is. So you can find it at a certain distance and then it decreases. Okay, so if we summarize what I just discussed to you, maybe I can summarize it in this one. So Louis de Broglie proposed the dual nature of matter, and then Schrodinger came out with an explanation about applying it to proton, and then Werner Heisenberg proposed the uncertainty principle. Okay, so Heisenberg, Born, and Bohr. So what they do is they come up with the probability state, the probability where the region where you can find the electron. Okay, so this one, what I'm showing here to you is just because of the wave-like properties of human. So in the beginning, we could say we start with one proton hydrogen, and then Schrodinger divides it into the so-called quantum mechanics model. Heisenberg, I don't know if you watch this so-called Breaking Bad. That's the code used by Walter White. Okay, because in the uncertainty position, uncertainty principle, we cannot tell the position or momentum at the same time. We can know position or momentum accurately, but not simultaneously. Okay, so if we're going to look at the summary of how the atom was described, or we could say evolution of the atomic model. So we start with Dalton, okay, and then we have Thomson, the plum pudding, and then Rutherford in the nucleus, and then Bohr, the planetary model, and what we have right now is Schrodinger equation, the quantum mechanical model. But that doesn't end here. It's just the start of what you need to know, okay? Because what we're going to discuss so far is the quantum numbers that was assigned, or we could say described. Now, this slide here, this is the summary of what the quantum numbers are. So maybe we go first in each of them and then we go back to this slide. Okay, because if we're going to tell overall what's the quantum numbers, there they describe the orbital an electron would occupy. And there are 4 quantum numbers, of which 3 of them is enough to tell you where your electron is most likely is. Okay, so the first quantum number, the second quantum number, the third quantum number, and the fourth quantum number. So we're going to go back to this what we call slide as we go on. Okay, but maybe I have to what we call take a break. I cannot go on and on like energizer. So 5 minutes. Okay, please come back. because most of the questions that you have in your quiz will be like this one. Okay, 5 minutes because my voice, I cannot go on and on. So 5 minute break. Going to look at the four quantum numbers. We have the principal quantum number, the azimuthal angular quantum momentum quantum number, the magnetic quantum number, and the spin quantum number. Okay, so as I told you, the three define the wave function for a particular electron. So when we say wave function, that's where you will probably find the electron. And the fourth quantum number is just the magnetic property of the electron. Okay, so we go with the first one. So before we go with the first one, we can also say that when we have a wave function, it's going to be described by the first three quantum number because it refers to what we call an atomic orbital. And an atomic orbital describes a region of space with a definite shape where there is a high probability of finding the electron. Okay, so we look at the principal quantum number. So this quantum number is the one on which the energy of an electron in an atom primally depends. The smaller the value of n, the lower the energy of the electron, or the what we call energy level, and the smaller is the orbital. So we could say in terms of S, this refers to the size. Because the three quantum numbers that you have, that can also refer by 3s. Now, the principal quantum number or the principal quantum number as described in other book, that's usually the energy level. And it can have a value from 1 to infinity. Now, the number that we have here, this is the one refers by Niels Bohr energy level. And in the periodic table, it refers to the row of periodic table. First quantum number, second quantum number, third quantum number. Or what? Quantum number 1, okay? Or n equals to 1, n equals to 2, and then n equals to 3, and go on as you go, okay? Filling up the thing. So the higher the energy level, the higher the energy of the electron. As n increases, the energy difference between the adjacent energy level, we could say decreases. So what we could say, n equals 2 is much larger than n equals to 1. And n equals 3 is much larger than n equals 2. Okay? So it calls the shell. In some book, they designate it with uppercase, but usually we just use the number. Now, the next one that we have is the angular quantum number, angular momentum quantum number. Okay, so this quantum number distinguish orbitals of a given n or shell having different shapes. So if the first one is size, this one is shape in terms of what we call the S. So the angular momentum quantum number indicates the shape of the orbital, the region of space occupied by an electron. And the values of this L depends on the N value. So what does it mean? If you have principal quantum number equals to 1, so 1 minus 1 will give you an L value that is equals to 0. And if you have n equals to 2, you have a principal, an angular momentum quantum number equals to 1. Now, each of this value refers to shape. Okay. So if you're going to look at them, we can design small letters to this one. When L is equals to 0, you could say it's an S. When L is equals to 1, it's a P. When L is equals to 2, you can design it as a D. When L is equals to 3, you can design it as an F. The way I ask my student, because you're going to see different shapes on that as we go on. This is a sphere. P is for peanut. D is for a double peanut. And F is for flower. I don't know if that makes sense, but I can jump in and tell you why I said that. See that? So that's the sphere. This is the peanut. Is it really a peanut? Okay. So that's the what we call p orbital. And this is the double peanut, except for this one. And this is the f orbitals, the flowers. So you can see the S, the P, the D, and the F. So sphere, peanut, double peanut, flower. We're going to discuss each of that. Okay. What we do now is just the shape. So if you have one S, so that means you have principal quantum number 1 and L that is equals to 0. If you have 2S, then you have N equals to 1, L equals to 0. And if you have a 2P, N equals to 1, L is equals to 1. So those are the information that these quantum numbers convey. Okay? So we were just in the second quantum number. So let's go with the third one, the magnetic quantum number. So you have the size, the shape, and this one, I'm going to maintain the S, the spatial orientation. So this is N, this is L, and this is M sub L. So this quantum number distinguish orbitals of a given N and L, that is, of a given energy and shape, but having different orientation. Okay? So the magnetic quantum number depends on the value of L, and they can have any integral value from negative L to positive L, including 0. So each different value represents a different orbital. So for a given subshell, there will be what? 2L plus 1. So what does it mean? If your L is equals to 0, how many orbitals do you have? You only have one orbitals. And that's, we could say, the S orbital. Now, if your L is equals to 1, you will have what? 2 times 1 plus 1, you're going to have 3 orbitals. And you have 3 p orbitals. And what are those, what we call the 3 orbitals that you have? You can designate them as negative 1, 0, and 1. So when when L is equals to 0, the value that you have there is just 0. Okay? So when your N is equals to 2, you can have 2 L values, right? If you have it like this. And the designated orbitals that you have here will be 1s, no, 2s, and this is 2s, and this one is 2p. And if you're going to look at what are those orbitals that you have here, so you can have a negative 1, 0, and 1. For this one, you only have 0. So if you're going to combine the quantum numbers for this, you can have how many set of quantum numbers? 2, 1, negative 1, 2, 1, 0, 2, 1, 1. And for the s orbital, you can only have 2, 0, 0 as the set of quantum numbers. Still with me? Because this is the time where everybody was, huh? So always remember that the value of the quantum numbers depends on the previous quantum number. Okay? So remember, n is anything from 0 to infinity, not 0, 1 to infinity. How do you do that? Infinity like that. And the value of L would depend from n minus 1. Okay? So whatever's the value of your n, you can have different value of that. So you can have from 0 to n minus 1. So usually if n 1 is minus 1, then you only have what we call 0 as the value. Okay? And then the m sub L just depends on negative L, 0, and positive L. Now this is enough to give you an orbital. Okay? So when n is equals to 3, you can have 3 values of L. 0, 1, and 2. Okay? So when L is equals to 0, your only m sub L value is 0. When L is equals to 1, you can have 3 values. When L is equals to 2, you can have 5 values. So if ever we're going to summarize what we're doing, this is what we have. So the first quantum number, the second quantum number, and the third quantum number. Now, if you're going to write this in terms of the orbitals, you will have it like that, like this one, and then this one is like this, this. And each of the orbital can occupy at most 2 electrons, like this one. Some sort of that. Okay? So if we rearrange this one, so this is how the Bohr model looks like, but with a specific number of orbitals. So you have here 1, and then you have here the s and the p orbital, and then you have here the 3, okay? And here you have the 4, the n equals to 4. So as you could see, the higher the n, the bigger is the size. Or we can also do it in terms of the house. When we say n, it refers to the size of the house. The higher the n, the bigger the house. The L is the shape of the house. So a 0 would have this house shape, a 1 would have this house shape, a 2 has that house shape. The M sub L, that's just the orientation of the house. Okay, now the last one that we have, that's the spin quantum number, and its value can either a positive 1/2 or a negative 1/2. So you have the 3 set of quantum numbers, and m sub s can either be what? A positive 1/2 or a negative 1/2. So what does it mean? One set of quantum numbers has at least 2 set of quantum numbers which can be differentiated by either positive 1/2 or negative 1/2. So for instance, 1, 0, 0, what's the orbital for that? So that's just 1s. Okay? But you can have two sets of quantum numbers for one s orbital. It can be 1, 0, 0, positive 1/2, or 1, 0, 0, negative 1/2. So that's what it means. Okay? Now, let's try to do this one. Which of the following numbers are permissible? So all you need to do is apply what you have learned about the quantum number, where the next quantum number depends on the previous quantum number. How about number 1? What if we say that this is not permissible? Why? When I have n is equals to 4, the value of L can either be from 0, 1, 2, and 3. Because L is always equals to what? From 0 to n minus 1. And 4 is not possible. So this is the one that messed up the set of quantum numbers. How about the second one? So we could say this is not. Okay, so this one is good. Third one. But what messed this up? Your value can either be this or this, but not this one. Now, when n is equals to 2, your L value could range from 0 to 1. And since 0 is there, so that means that's checked. And if you have 0 here, the value of your m sub L will just be 0. Okay? So n equals to 5, L is equals to 3, yes. M sub L equals to negative 3, yes. Because the possible value of your m sub L is what? Negative 3, negative 2, 0. Oh, negative 1, 0, positive 1, 2, and 3. And negative 3 is one of them. So this one is also possible. Okay? Now, as I've told you, the shape, although we jumped it already, so an s orbital is spherical. A p orbital has two lobes along a straight line through the nucleus with one lobe on either side. That's why I say sphere, peanut, okay? And then a d orbital has more complicated shapes. So this is the sphere, okay? And this is, we could say, the peanut. And then this one, we could say the double peanut, and then a dumbbell with what? A donut. There's a donut there, and then there's a dumbbell inside of it. And then this one is the flower. So those are the magnetic shapes. So as I told you, we're going to go back to the one that we have earlier here. So if it's the first quantum number, the principal, it refers to the distance from the nucleus. It's called the principal quantum number and the energy level of the electron. The second quantum number, which is the angular momentum, that's the orbital shape. Okay. And then what you have here, it can be an S, a P, a D, or an F. So an S is equals to 0, a P is equals to 1, a D is equals to 2, and an F is equals to 3. Now the 3 here is the spatial orientation. That's your magnetic quantum number. And it's just the shape that you have there in terms of the X, Y, Z, where you have. And then the last one is the number of electrons of orbitals. That's the spin quantum number. So you can either have a 1/2 or a negative 1/2. I'll try to look some questions so you can go over on how to review this thing. So I have to open the, we could say, we still have a lot of time, the reviewer that we have, June 1. So do you see this example question? So I would suggest you go over them. I'm just trying to give you more examples on how the question would look like for these quantum numbers. So as you could see here, I told you there's a lower, longer there in terms of the color. This one, I may not ask you about this in terms of the order. I don't want you to memorize, okay? So you might be asked about personalities, which we discuss a lot. So maybe I just turn this off. So you'll be the one who, I want you to guess. Okay? 5D. So D is what? D is equals to what? 2. So when D is equals to 2, that means L is equals to 2. So the M sub L value can be from whatever's the negative L to positive L. So negative 2, negative 1, 0, 1, and 2. So in this case, what's the possible value that you have here? Can I say C? Does that make sense? I think Talina is the only one with us. Andrew, Hamsira, are you there? Okay, good. Now, you know why I should C. Because where do we get the M sub L? I try to, I hope I can, no, it's a signature thing that I have here. No, no, that one. So remember, M sub L is just equals to what? Negative L to positive L, including 0. Okay, that's why we end up with 2. Because remember, what's the value of L when you have a 5D? Okay, so remember in the quantum number, what do we have? In the set of quantum number, you have the N, you have the L, you have the M sub L, and the M sub S. And usually the first two is the one that is given. This one is a letter, N is a number, and L is always a letter that corresponds to a number. Okay? How about this one? All of the following statements about the quantum numbers are true except letter A is true. N may take integral values from 1 to infinity. L may take integral values from 1 to n minus 1. I think that's false. To make it true, you have to replace this 1 with 0. Okay? And then M sub L has 2 times L plus 1 possible value. That's true. Because if M sub L is equals to 0, I mean, if L is equals to 0, your M sub L will always have one value, which is 0. Okay? And then M sub L may take integrals values of positive L to negative L, including 0. That's true. And M sub S may take only the values of 1/2 and negative 1/2. So these are the type of questions that you will be asked. And I want you to be sure points on that. Okay? So how many values are there for the magnetic quantum number when the value of the angular momentum is equals to 4? Anyone? What is your answer? How many values are there for M sub L when the L value is equals to 4? So that will be what? 4 times 2 plus 1. And the answer is E. You got that? Give me a thumbs up if you got that. Why the answer is 9? Just to let me know you're still awake there or listening to the session. There's only 3 of you here now. And if you have a question, you can ask. I think it's in the reaction that you have there. Now, how about this one? So this is now the reverse. You're given the quantum number and you're asked what's the subshell. So the subshell is made up of the principal quantum number, which is the shell, and the angular momentum quantum number. That's the subshell. So that means the two quantum numbers with the second quantum numbers in letters. So all you need to do is get the 5 here and determine what's the symbol when L is equals to 2. What's the letter that we use when L is equals to 2? L0 is 1, L equals to 1 is what we call, L equals to 0 is S, L equals to 2 is P, L equals to 1 is P, and L equals to 2 is D. The sphere, peanut, double peanut. So the answer here is 5D. So I would suggest go over the questions that you have here in terms of the quantum number. You still have 1 hour to go over this thing. Okay? Now this one, this is the thing that maybe we didn't tackle directly, but you can get the number of orbitals by just the n. What's the formula there? Number of orbitals by just looking at the n. So I'm going to give this to you. Number of orbitals equals to n squared. Why? When n is equals to 1, what is the number of orbitals? You only have 1. You only have 1s. When n is equals to 2, what's the number of orbitals? So 2 squared, that's 4. So you have a 1s there and, no, not 1s, a 2s and a 2p. How many orbitals a p has? 3 orbitals. So when n is equals to 3, so that means 3 squared, you have 9 orbitals. So that means you have 3s, 3p, and 3d. So this is 1 orbitals, this is 3 orbitals, and this is 5 orbitals. Remember, this was 0, and this is -1, 0, +1. This is -2, -1, 0, +1, and +2. And each of them is an orbital. You got that? Because you can also be asked, how many electrons when n is equals to 2? So what do you do if this how many electrons? So whatever's n squared, you just multiplies by 2. Why? Because each orbital can accommodate at most 2 electrons. So what do you think? Going to be a busy day for you. Are you ready? So, well, as I could say, you need to practice.